In this video, we're going to solve a popular problem using heaps, and the problem is finding k largest elements with mean heap. Basically, the problem statement here is that given an array, we want to find the k largest elements. And in this example, we're going to use the array 10, 30, this array that you can see here, and try to find the three largest elements. So one way we could solve this, which would be sort of the brute force way. So we can start with that. So here for the brute force way, the brute force method that you can use here, the brute force method that we can use here is basically sorting the entire array. So sorting the entire array. This is going to be the brute force solution. In sorting the entire, we're going to basically sort the entire array and pick the top k elements. But one problem with this one, with such an approach, is that it's going to take O of n log n time. So it's going to take the time complexity of O of n log n time. Let me just write it correctly here. So it's going to take O of n log n time, and which can be slow, especially when you're dealing with a large array. Imagine dealing with an array that has about 1,000, 10,000 elements. With this brute force solution, you basically have to go through the entire array, sort it, and then find the top elements that you want. But the more efficient solution here at the moment is going to be using a main heap. So the other solution that you can go is basically using a main heap. And how this is going to work is for using a main heap of size k. So we have to specify the size of the main heap. Then we start sorting from there. So basically the plan here is we're going to maintain a main heap of size k. So we'll maintain, we'll use a different color here. We're going to maintain a main heap of size k. And in this case, let's maintain a main heap of k is, let k be 3, right? A size of 3. As we go through the array, we're going to add elements to the heap. So whenever the heap grows larger than k, we remove the smallest element, making sure that only the largest k elements remain in the heap. So to go through the solution, we just try and visualize it. And I'm just going to get the subarray here and we can use it. So we have a subarray here, and we're going to start with the array that we're going to start with here is going to be the first three elements. So the first three elements here are 10, 30, and 20. So let's start with those here. We have 10, 30, and 20. And to arrange these elements in a binary tree, how they are going to look like is we're going to have here, we're going to, in a main heap, the smallest element is the one that we usually start with. So we're going to have 10 right there. Then we can have 30 here. This should be 30, and 20 on this other side. So here we're going to have 20, and we can get rid of these other ones. So we get rid of also the 5. And this is what it's going to look like when you have the first element. So this is what the first main heap structure is going to look like when you get the first three elements. Since our initial heap, since this is our initial heap that we have now, we don't need to make any adjustments as of yet. The next step is going to be now moving to the next element. In this case, in our array, the next element here is 15. And to keep the largest three elements, like you mentioned earlier, we're going to compare 15 with the root. And the root, as we know, here is the smallest element. And if that element we're trying to compare with the root is larger than the root, then we replace. If it is not larger than the root, we ignore that element. But in this case, since 15 is greater than 10, our heap size is already 3, so we're going to remove 10 and insert 15 here so that we can keep the largest elements. Now this is going to be our new binary tree. Actually, we can just have a different copy so you can see how the entire process is going. Now here, instead of 10, we're going to have 15 as our new, this is going to be our new structure. And in our array, this is also going to change. And now the array is going to have 15, 30, and 20. So this is going to be the new array that we have. The next thing we're going to do is we're going to now consider the next element. In this case, the next element we're going to consider here is 5. Considering the next element 5, what we'll do basically is we're going to compare 5 with the root. And once we compare 5, we realize that 15 is larger than 5. So we're going to ignore 5 in that case. And our main heap is going to remain as it is. So we skip that element. Moving to 8, 8 as well is still smaller than 15. So we're also going to go ahead and ignore that, and our heap is going to remain the same. So after processing all the elements that we have in our array, the final heap is going to contain the 3 largest elements from the array. So what we're going to have is this is going to be the final heap that we're going to have. So from this to this, and also from this to this, these are going to be our final heap. And with this min heap approach, we're going to store the largest elements, making our solution more efficient, especially with the large arrays. So if you're dealing with a large array, it's going to basically be a more efficient solution. And the why this is going to be even more efficient than having to sort through the entire array is that this is going to have a time complexity of O of O of n log k, and k being the size that we decide to be the size of our main heap. In this case, it's 3 because we're getting if the number of elements we're getting is 3, that's what we get, right? And that is basically it. That's how we find the largest element with main heap. And just to understand a lot more about the complexity, this is faster than this one. Simple reason is when you're using the brute force solution, we have to iterate through the entire array. But when you're using the min heap solution, we only take basically we choose the size of the main heap. Then from there, those are the only elements we're going to be dealing with, right? So that is it, and I'll see you in the next one.